Good. Our agenda is principal component analysis, which falls in the category of feature extraction methods, as I already mentioned. So dimensionality reduction, as I already mentioned, can be done in two ways. One is feature selection, the other is feature extraction. In the case of feature selection, what we do is we select certain features out of the available set of features. And feature selection can be done in primarily two ways. By using an appropriate ranking mechanism, such as information content information gain, which is called feature selection using filter approaches. Feature selection using wrapper is another class of feature selection where we bring in the notion of the classification or use a classifier in the context of feature selection. We select those features which will be the best feature set to do that task at hand, which is classification. This is called a wrapper approach to feature selection, and our topic is principal component analysis, which falls in the category of feature extraction methods. Feature extractions can be compute new features out of existing features, just like the example that I gave a while ago, which is the BMI is essentially computed from your height and weight. Likewise, can we get into computed features rather than using the original features? And that's what feature extraction is. This is again another method for dimensionality reduction. Before we get in there, there is an interesting observation called curves of dimensionality, right? Increasing the number of features will not always improve the classification accuracy, and this observation is called curves of dimensionality. In practice, inclusion of more features might actually lead to worse performance that you can see as in the, so your performance may improve for some time, and then if you add more and more features to the definition of your objects under consideration. So if you add more and more features, your problem context, what is going to happen is, yeah, for some time it will improve and then it will come down. It's primarily, you can observe it from here. Say for example, let's assume that this is a feature dimension, one-dimensional feature. One-dimensional feature, you have your entire data values you bucket into three buckets. You can, I mean, for simplicity, you can assume that a feature can take only three values, three unique values, right? The feature can be either what you call medium, low, or high. So three values, right? That's three value features. This is a one-dimensional thing. If you look at a two-dimensional, again, let's assume that the features takes typically three values only. So you get 9 combinations, right? 3 here, 3 here. You get 9 combinations. So 3 raised to 2 bins you get, right? And if you extend that to 3 dimension, you get 3 raised to 3 bins. If you extend that to n dimensions or d dimension, what you get is 3 raised to d bins, right? N dimension 3 raised to n bins. Which means that if you want to represent your data with all possible values for all these combination of features, you need to have enough of data. Which means that you have a larger, pretty large, what do you call, sized data space or bin space, or rather, it can in the most conventional form, you can call that a grid space, where every combination has to be there for your data to be well represented. Which means that you need a lot of training examples. You need a lot of training examples so that everybody is represented, every combination is represented. And if you do that, right? If you do that, you have a lot of intricate details over your data. And do you remember the notion of overfitting, which I mentioned a while ago? So if you train your machine with all the potential data and you train the machine with all the potential details, it's highly likely that your generalization performance will come down, right? It can potentially lead to overfitting of data because you have a lot of details. You don't need as much details as you want. And one of the problem with this kind of what you call adding more features to the problem context is right, the number of training examples. You need a lot of data because every combination has to be there, and if every combination there, every other detail out there, the machine can generally overfit and performance can come down, right? So that's another explanation to why the cost of the dimensionality happens and why it's not very interesting. So adding every other detail may not always help you in your learning problem, and that particular aspect is called the cost of dimensionality, especially observed in the case of classification problems. Right. So objective can we choose an optimal set of features of lower dimensionality to improve the classification accuracy is the objective. It's called the dimensionality reduction problem. Instead of considering every other feature, can we bring down the feature set size? All right. Two approaches. I've already mentioned that to you. Dimensionality reduction can be done in two ways. One is feature selection on the right side. You see, choose a subset of the original features. See, if you have got x1 to xn, these are the features. This can be age, this can be the salary, this can be the neighbor's kid's name, this can be the neighbor's name, this can be the name of the road in front of your house, this can be like what you call your closest friend's name in the 10th standard, this can be whatever. You got 10 features out there, out of which you choose a subset. You choose only like, say for example, k, which is less than n. So that's what it is. You choose, this is called feature selection. And choosing certain features, which essentially means that you reject certain features. Right? That's what it is. And the approaches can be a filter-based approach, which is a ranking-based approach without the problem context like classification brought in, or it can be a wrapper-based approach, which uses a classifier, as I already mentioned earlier. And the second class of dimensional reduction algorithms are called feature extraction methods. Finds a set of new features through some mapping f from the existing features. So, for example, you have got n feature, whatever, right? Your data is represented x1 to nn. Xn is represented in terms of, as I already mentioned, this feature can be represented in terms of etc., etc., etc. Can I represent my data in terms of k, which is less than n, which is essentially the problem? Can we extract? Can we find a new mapping from the available set of what you call available set of features to a new set of features, which is computed, which is essentially a mapped feature set. All right. Here, the easiest way to understand this will be like from weight and height you compute BMI. So it's an example for extraction of new features, computation of new features. All right. And if you want to do such a computation, a feature extraction, the easiest method is a linear combination. Can you do a linear combination of features? Linear combinations are particularly attractive because they're easy to compute and analytically tractable, traceable, mathematically simple structures. Given x in Rn, all right, can we find a matrix of dimensionality in by k? And let's call that matrix U. So the new representation y may be U transpose of x. All right. So x can these vectors be mapped onto onto the U the space defined by spanned by U the matrix U, and then you get a new set of representation. Essentially, it projection from the n-dimensional feature space to k-dimensional space. That's essentially the point. Can you do that? All right. So can we do a linear combination? Essentially, like you have seen, like we are doing a linear combination by mapping onto the space defined by this matrix U. Right. That's the feature extraction. That's in mathematical form. That's what it is. All right. From a mathematical point of view, finding an optimal mapping y of essentially which is fx is equivalent to optimizing an objective function, and PCA does this. So can we minimize the information loss when you project an n-dimensional space to a k-dimensional space? The goal is to represent the data as accurately as possible, but that means no loss of information if possible in the lowest dimensional feature space, right? That's what it is. Can we do mapping without the minimal loss of the data, right? Let's represent x and Rn as a linear combination of an orthonormal set of n basis vectors v1, v2 up to vn. So we are considering a set of basis vectors, n basis vectors, which are labeled as v1 to vn. So this is basically like there's a space spanned by this basis, which is v1 to vn in the Rn space. All right. So v1 to, and we assume that these vectors are orthonormal. Basically, like vi dot vj is equal to 1 if I is equal to j is equal to 0. Basically, like they are normalized, and vi dot vj is equal to 1 when I is equal to j. Otherwise, they are 0. They are orthogonal also, right? It's orthonormal. As presumed that they are orthogonal also, right? So we want to represent the vector under consideration x in the new basis. How do you do that? This is what you do. X can be represented as a combination of xi vi, right? Where xi is essentially like the projection of the component of x along the dimension v1 or vi, right? x1 will be the component of x in the dimension v1. So this is basically like you represent your vector in the new basis, right? In the new basis, there you can see that x v1. So where all these xi's, these particular xi values will be, if you look at it, that will be like the projection, right? All the xi's will be projection of basically like projection of what we call x onto vi, right? And normalized by the the vector vi. And if we presume that the basis vectors, these are normalized, so it's essentially like kind of we are normalizing that. So this is a direction. Vi by vi transpose vi is a direction, and you project x onto that direction. That's what it is. And we know that vi dot vi, it's basically what is vi dot vi? This you can, if you look at it, it's the length of the vector, right? Normalized, right? It's the length of the vector. Vi normalized in that length by the length of the vector. And vi dot vi, we know that we have already stated that these are orthonormal vectors. So vi dot vi will be 1. So vi dot vi will be 1. So we don't have to do that. So this is basically like it's basically x dot vi. So x dot vi. So xi will be x transpose vi. X transpose vi. The projection of x onto the dimension of vi. That's that we can easily understand from your basics on linear algebra. That's something that you've done at the early part of your course in the induction, right? So this is what it is, and you represent x in terms of what you call, represent x in the space spanned by the basis vectors v1 to vn. That's what it is. Now the natural question is, so the PCA, what are we looking at PCA? PCA, we are looking at the projection with the minimized information loss. We want to get that projection with the minimal information loss, right? PCA seeks to represent x in a new space of lower dimensionality using k basis vectors, where k is less than n, the current dimensionality. So I want to get an x cap, which is essentially a representation of x. X cap is essentially a representation of x only in k dimensional space, because I am looking for a dimensionality reduction with mapping, right? So let's look at those vectors, the vectors ui's, which are essentially the basis vectors for that dimension, where ui spans over 1 to k. So we have u1 to uk, and what I do is I need to get that yi ui pair. Yi ui is essentially like yi will be essentially, if you look at it, yi will be the projection of what you call the x onto the ui dimension, which is essentially the basis over which we want to represent. And what is our agenda? We want such a representation. We want an x cap such that yi ui plus etc. This is what we are looking for, right? This cannot be. This is essentially where each of these yi will be the projection of it will be computed like this. It will be the projection of x onto that ui, right? So x dot ui will be yi. That's what it is, because we assume that let's assume that ui's are orthonormal vectors. Let's assume that. Otherwise, you get to this expression. That's what it is. And what's our agenda? PCA is looking for that particular projection where the information loss is minimal. We want to minimize what the loss, basically like x minus the second norm, basically the minimize the information loss, right? You minimize the information. That is essentially the second norm. All right? You want to minimize x minus x cap, and the second norm of that needs to be minimized. How do you do that? This is an optimization problem. We want to get a representation. We want to get that representation where what you call the difference, basically like the second norm, the difference between x and x cap is minimized. All right? How should we determine the optimal lower dimensional space basis vectors such that the information loss is minimized? That's a question, right? This can be like the optimal lower dimensional space can be defined by finding the eigenvectors ui of the covariance matrix of data. We'll understand why we do this. Finding the eigenvectors ui of the covariance matrix of you compute the covariance matrix of the data, right? And then what you do is you can actually find the eigenvalues and eigenvectors. So you can compute the eigenvectors choosing the k largest eigenvectors of ui. We can choose the k largest eigenvectors of ui corresponding to the k largest eigenvalues. We refer them, these largest eigenvectors, as the principal components, and what we do is we project the data onto the dimensions where for corresponding the largest eigenvectors, corresponding to the eigenvectors corresponding to the largest eigenvalues. So essentially the principal components, and this is essentially the idea, right? Suppose we are given a data set x1, x2 up to xm n dimensional n by essentially like n dimensional vectors. What you do is you essentially compute the sample mean, and then you can subtract, basically like you send the data to 0. So you send the data to 0, and then you can compute the covariance values, and then compute the eigenvalues of the covariance matrix, right? So you get the corresponding eigenvalues and the eigenvectors, right? Once we do is we can, most of you get easy implementations there, right? This is symmetric. U1 to UN will be an orthogonal basis. That's the definition of eigen. The eigenspace is an orthogonal. The eigenspace, the space spanned by the eigenvectors is an orthogonal basis, right? What you do is you essentially you get that representation. Essentially, you're representing, right? You have to normalize your vectors. So xi minus x bar can be represented as, right, yi ui, where yi ui is essentially the eigenvectors. You compute you compute basically you represent your vector in terms of those in the dimensionality of those vectors, and where yi is essentially, I told you in the earlier case also, x minus x bar is mapped onto ui by ui dot ui, because since ui dot ui this is orthonormal, right? Since this is orthonormal, what you do is you get is xi dot xj is essentially your data projected onto ui. This is what you've seen here also, right? Your data, I've told you this here also, right? Your data is projected onto this. Essentially, your data is projected onto the basis or the vectors under consideration. So this is what it is. X dot vi. That's what you do. Instead of x, you have the centered around 0. So basically, what you do here is just go here. You compute the eigenvectors corresponding to the covariance matrices, and then what you do is you project that onto ui, and since this is normalized, so these are orthonormal vectors, what you get is this, right? So each of these yi's can be computed. And what is our agenda step? Dimensional detection step. Approximate x using only the first k eigenvectors. This is use all the eigenvectors. You don't have to do that. You just take enough of them. Approximate. So we have this as the original representation. You don't do that. You minimize. Basically, you reduce. You represent only in terms of the first k eigenvectors. Essentially, you call the principal eigenvectors. So you do take k of them, right? So your representation will be like your representation will be like this, where u will be your the original. So you need a matrix u, which will be the first principal components, which are essentially the eigenvectors corresponding to the k maximal eigenvalues. Right? That will be the columns of u are the first k eigenvectors of the covariance matrix. You choose that, and then you do the mapping. Right? That's what it is. The linear transformation from R into Rk, which performs the dimensional reduction, is U transpose X, where the transformation is basically this is basically the matrix of eigenvectors, the principal eigenvectors, and then you project them, and then you essentially get this transformation. Right? So the rows of Ut are the first k eigenvalues of the covariance matrix. So that's what is basically done in PCA, and just a solid example, we'll come back and look at this critically, what is happening over here. Compute the PCA for the data set. You have some data points given here. What you do is you find, initially your first step is you can actually center those points, compute the covariance matrix. You can easily get you can compute the covariance matrix of it. You compute the eigenvalues and eigenvectors for the covariance matrix. You get eigenvalues and the corresponding eigenvectors you get. So what you do is, for each of these data points, you compute the dot product. So you get normalized eigenvectors unit length, and then you project. Right? That's what is happening. Right? You project your data onto those dimensions. Right? If you want a 2-dimension, you get 2-dimension. If you want a 1-dimension, you can get a 1-dimension transformation. Taking only the maximal eigenvectors corresponding. Eigenvector corresponding to the maximal eigenvalue. That's what is happening in PCA. Right? Geometric interpretation. PCA chooses the eigenvectors of the covariance matrix and corresponding to the largest eigenvalues. So in the covariance, what is essentially the covariance? What is being captured in the covariance matrix? What is the semantics of covariance matrix? Covariance matrix, the diagonal elements will contain the variance, and the off diagonal elements will be the basically the variance across those dimensions. Right? That's what the covariance matrix is about. So the eigenvectors of the covariance matrix will essentially correspond to the variance of the data along the eigendirections. That's what it is. Right? That's what the meaning. So if you are computing the computing the what we call the eigenvectors of such a matrix, which is essentially represent the variance of data, and those dimensions will be essentially like, see, if you look at it from the spectral theorem, you know that along those dimensions, like when you actually like what you call when you are finding those dimensions, and essentially if you are looking at that eigen decomposition, what is happening like on each of these values, the corresponding eigen values are essentially the what you call the correspond to the value of that particular, basically like, I mean, in our case is essentially the variance of the data across the dimensions, and you are essentially looking at the eigenvectors for which the values are maximal eigenvectors. So essentially, when you are looking at the eigen values and eigenvectors of the covariance matrix, essentially you are looking at those dimensions where the data variance is maximal. You are looking at the principal ones, the ones where the variance is maximal, right? And looking at those dimensions, we're looking at those dimensions, right? When looking at those dimensions, what you essentially choose is the dimensions over which the maximal dimensions or the dimensions over which the variance of the data as per the available data, the variance is maximal. So you're identifying the dimensions where the variance of the data is maximal, right? And then you project data onto those dimensions. So therefore, PCA projects data along the directions where the data varies most. So if you look at it, so we are essentially like we are looking at, and we'll come to this slide later. What is our optimization problem? Optimization problem is x minus x bar needs to be minimized, right? That's what we call the reconstruction error needs to be minimized, and our x bar is essentially we are choosing those directions where the variance is essentially the maximal, right? And we are choosing those dimensions where the variance is maximal. If I want only one dimensional representation, I take the dimension for which the principal component for which the principal component is essentially representing the eigenvector for which the eigenvalue is maximal, which means that I'm taking the direction where the variance is maximal at, and then my data is projected over those dimensions, then, right? And then what I do, if I want one more dimension, I take the next one. I keep adding. So essentially, I will give more importance to directions where the variance of the data is maximal while I taking the representation. Essentially, if I take all the eigenvectors, I get a representation where the reconstruction error is minimal, is basically close to 0 or 0. And if I choose to omit certain dimensions, I am omitting those dimensions where the variance is minimal, right? I am choosing those dimensions where the variance is maximal, right? Which means that my optimization is is protecting my needed semantics, which is essentially the minimal loss of what we call information, right? The variance is I'm protecting. I'm choosing those dimensions where the variance is maximum, right? That's how it works. And your natural question is, how do you choose k? Typically, right? You choose k in like this. You choose k like this. K is typically chosen based on how much of information variance you want to preserve. Do you want to keep everything? If you want to keep everything, you can choose all the eigen vectors. If you don't want to keep everything, I want to provide a threshold. This is T. This is basically like the sum of eigenvalues, right? Sum of the eigenvalues of covariance matrix, and sum of the eigenvalues for all the eigenvectors, sum of the eigenvalues for the first k eigenvectors. So I'll take a fraction of sum over all k at the numerator, and at the denominator I'll have sum over all n, all the eigenvalues, right? So I take this fraction and I put a threshold, and I say like, if the fraction is, my agenda is what we call greater than t, I choose k in such a way that this particular inequality is satisfied. I choose k in such a way that this particular inequality is satisfied. If t is equal to 0.9, which says that we want to preserve 90% of the information, or that means the variance of the data, in that case, I need to choose k in such a way that what we call this particular fraction is greater than 0.9. Right? This fraction is greater than 0.9. Right? That's what it is. So, and this is where that you get an insight into optimization. What is this? If you understand a little of eigen decomposition, you must have realized what is lambda I. Lambda I is basically what is lambda I? Lambda I's are essentially the eigen values. All right, eigen values of what? Eigen values of the covariance matrix. In the covariance matrix, the diagonal elements are the variance values. Some of the diagonal elements are the trace of the covariance matrix. sum of the, I repeat, sum of the diagonal elements of the covariance matrix or the trace of the covariance matrix is equal to the sum of the eigenvalues, right? That's linear algebra. So sum of eigenvalues is equal to sum of variances. Good? Alright? Sum of variances, which are essentially the trace of the matrix, of the covariance matrix. And what do we want to minimize? We want to minimize, right, the information loss. We want to protect those dimensions where the variance is maxima. So what is this? What essentially this does? It's essentially like I want to choose the lambdas or the directions in such a way that, right, the variance is, I want to protect those dimensions where the variance is maxima, right? That's what I do here. That's optimized. That's how we address the problem of minimal information loss in the case of PCA, right? From a theoretical understanding, this is what is happening, and this is why we do like this. And the computation of PCA is very straightforward. You take the data, you compute you can normalize the data, and then you compute the the eigenvalues and eigenvectors. You compute the covariance matrix, and you compute the eigenvalues and eigenvectors corresponding to the covariance matrix, and you select those dimensions where. And if you want a three-dimensional representation of your data, what you do is you choose the eigenvectors corresponding to the maximal 3 eigenvalues, and then your data, every data vector is taken, and you take a dot product of every data vector with those eigenvalues. So essentially, you project your data onto those 3 dimensions, and you get the PCA represented values. And why do you do this? Because you want to. PCA is essentially like trying to optimize the information loss by projecting data onto those dimensions where the information loss is minimal, and this can easily observed from here because what you do here is essentially like this is a trace of the matrix, right? And this is basically like some dimensions, some diagonal elements, which is essentially like kind of part of the trace, right? You want to protect, you want to make sure that this fraction, which is essentially like what you keep to what you have, is greater than 0.9, which means that I don't want to lose a lot, right? I want to maintain all those dimensions where I don't lose out a lot on data. That's essentially the basic optimization that's happening over principal component analysis. And I hope I'll stop my recording here. And computing, it is very straightforward. Most of the packages do have easy ways of looking at this data, and I can take some questions and potentially do some interactions for it.